Hello everyone, today I'm gonna discuss power distribution system. Power distribution system mainly divided into four categories. It's first of here is a generation end, and this is a high voltage transmission end, and this is the green one is for distribution, and this portion for utilization section. So here only three type is mentioned here, but it is the user end. It can be defined as the utilization side. So here's a generation station. A couple of synchronous generator can be connected in parallelly in the power station, and the generating voltage is typically lower than the transmission voltage. Generation voltage could be 11 kilovolt to the 13 kilovolt. Sorry, it's 30 kilovolt. And then step up power transformer, three-phase power transformer used to convert the high voltage transmission line. It is actually AC to AC converter. And here we see that there is a high voltage transmission line, and it's the value could be like this. So typically 230 kilovolt transmission line is normally used for in any power system. And then here is the this is the three-phase step down transformer. It is also called the distribution transformer, because we have to step down the high voltage line, because at the end user, either where for the single user, so for the 60 hertz the phase voltage is the 120 volt, or the for 50 hertz is 240 volts, so it's a lower voltage. But here is a 230 kilovolt, so we must need to reduce the voltage. So here we need the distribution. Today we mainly focus in this green. This is the distribution section here, and this is the step down distribution transformer. And here there is a this is the for huge load for the industries or other big power load sectors. And this is the for customer. This is it could be the for a large building apartment, and this is for the single user or just at the very end user distribution. So here once again we need the transformer, step down transformer. It also called the distribution, because distribution section can be divided into two parts. It's a primary distribution and the secondary distribution. Here you see that from 230 to this side the voltage maybe is 66 kilovolt or 33 kilovolt, and is turned into 130 to 33 kilovolt, and then 33 to 11 kilovolt, or 11 kilovolt to 120, or 24 to 240 volt. So later on we'll discuss in details. Now go this is the same figure of the previous one. So is the power station, power generating station. This is a set of a power plant. This is the synchronous generator, and the three-phase transmission line is connected to the transmission line pole via a power transformer. This is three-phase step-up transformer, and this symbol of pole is for transmission line, and this is for the high voltage transmission line. And this pole, the symbol of pole for the high voltage distribution, and the voltage is gradually decreasing here, and the symbol of the pole size is also the changing. It means that the voltage is lower there and the voltage is higher over there. So this is the transmission substation. So, and this is the step down transformer actually. And then here is the distribution substation. This is a transformer is here in the substation. It could be equipped with the current transformer, potential transformer, step down transformer, yeah, and also the switch gear and the circuit breaker, isolator, switch, fuse. There's a multiple element. You can have the substation. And here is the distribution line is directly go through the this is the premises, and Here is another step down transformer for the residential household, and this is directly connected to the big, this is the industry, or this is the big large apartment is there. So according to the power load, or the number of uh, customer premises, the distribution voltage depends on the transmission uh, line voltage, as well as the transformer size. Let's go here. The same figure is mentioned here. This is the generating station. Is either 11 kilovolt or 13 kilovolts is commonly used. These two type of voltage, and 30 kilovolt is rarely used. So here is a step up transformer is 11 to 130 kilovolt. This is the primary transmission, and once again we need to reduce, and this is the 130 to 33. This is the step down three-phase transformer, and this is the receiver station, because this is large industry load that may be connected directly to the 33 kilovolt side, and then once again we have to reduce the voltage through the three-phase step down transformer, and this secondary one is 33 to 11 kilovolts. So this side is 33, this side is 11, this side 132, and this one is 32. And once again the distribution side here is the secondary distribution that is connected to the end user. So it's a 400 volt, it's a line voltage, so it's for 60 it's for 50 hertz consumer, and where is the line voltage is 230 volt. Sorry, the phase voltage is 230 volt, and if we multiply 230 into root 3 times, then we'll get 400 volt as a line voltage. So here we see that the generating in voltage is ranging for 11 to 33, but commonly used, as I say earlier, it's 11 or 13, and it's a three-phase synchronous generator, or it could be called as an alternator. And then the output voltage is step up to the transmission line, so step up to the transmission line. There is a multiple advantage of high voltage transmission line, because as the voltage is higher, when the voltage is high, and then the energy loss is low here, because we know is P equals BI, then I equals P divided B. If B is much higher, then I is lower, and then transmission line loss I square R is lower. So it's the benefit of high voltage transmission line, as the voltage is higher, and then the loss is much lower. So now we'll see the difference between single phase and three phase system. Here we see that this is the phase 1 started from 0 phase shift, and then the second one, because we know the phase difference theta equal to 360 divided n equal to 3 phase 3, then the difference between each phase is 120. So this is the phase 2, and here you see that this is the 120 lagging, and the third one is 240 lagging. So here's the phase 1, phase 2, and phase 3, and here is the for single phase system. This is one cycle. We see that there's a difference, because so for the higher load typically three-phase system is used. There is several advantages of three-phase and the single phase, because the three-phase power supply are more efficient, because it could supply more power, and also Also the consistency, how is defined the consistency, because of peak and dip, because here you see that in a cycle there's a 1 0 crossing point, 2 0 crossing, and 3 0 crossing point. But in three-phase system, like for the phase 1 here is a zero, it's a zero crossing, but other two phase have a value, so the power will never goes to the zero, but it crosses already three times in a single cycle. But here you see that for the phase 1 here is a zero crossing, the power is zero, but the total power is never zero, because here phase 2 have the certain value, and phase 3 have the certain value. So yeah, it's definitely have a value, it's not gonna goes to zero. So here is the big advantage, because the for the single phase it's on off, yeah, and so the power is on off, and it may interrupt the circuit operation. So, and the power and for the three-phase system, the power supply, the power provided is three times higher than the single phase supply, just only adding a single one additional wire. And for three-phase supply we use the less conductor material for the same power supply that's done by this single phase, because for the single phase one need to, this is a phase and this is the neutrals, it's a two wire. So for three phase you see that this is only three wire, or so four wire is needed. But for the same power supply that is done by the three phase, this is for single phase, then for single phase, and we need three three into two, six wire to supply the three phase done by the single phase circuit. So yeah, so the conductor material obviously is less amount of required for the three phase power supply system. So here is the clear difference between single phase and three phase. The definition: the single phase power operating in a single conductor, and it's a three conductor, and wave cycle is just only one wave cycle, and it's a three wave cycle, as you see here from the figure. And the circuit of connection is a single wire, it's a three wire, and ability to power transfer, so it's a three times higher than this. And the power failure, no power failure, because it's a frequent, it's called frequent because every time is going to zero and then zero, and here once again zero, this is zero crossing, this is zero crossing, this is zero crossing. It's frequent because this time is for 60 hertz, the time is 160, because t equals 1 divided f, so it's 160 second. Okay, so now efficiency, three-phase system is higher efficient than this. And application, so for single phase is for use for low load, and this is for to run a heavy load. Now we'll see the difference between star connection and the delta connection. As we earlier see, the for the star connection, the line voltage is root 3 times to phase voltage. Here this is the line current, this is the Y connected, and this is line current, and the phase current remains same. And whereas the line voltage and the phase voltage is related to the root 3 times, and just opposite for the delta connection. Here the line voltage, here the line voltage and the phase voltage remains same, but the line current is root 3 times bigger than the phase current. So it's for delta connection. Now let's see a small example here. So it's a supply end, and this is the load end, and this is the balanced load, and everywhere this is 8 ohm, 8 ohm, and 8 ohm. This is the load side. Yeah, and line voltage is given 480 volt. Yeah, line voltage for load, this is L for load, and P for primary side, it's a generation side. So load voltage is 480 volt. So in delta connected load, we seen earlier above, there is a here the voltage is same line voltage and phase voltage, so it's for load, and the phase and line is same 480 volt. We have to find this value, and then the current is I equal to E divided by Z. This is a phase value. Z is a impedance. There is no inductance mentioned here, so Z equals R here, and all the three phase is a balance is of 8 ohm, and the line current, it must be root 3 times of phase current. Here is the phase, and this is the line current, and the line current for the generation in is because is 103.92 ampere, and for the generation side is Y connected, star connected, so the phase voltage uh, is could be the EL line voltage divided root 3 times, because it will be lesser than the line voltage according to the formula. And then the power, the true power, P equals root 3 VI cos theta. Here cos theta equals 1 because all the resistive load, for the resistive load, the power factor cos theta equals 1. So here the formula is root 3 B IL is the line values of obviously cos theta. Here cos theta equals 1. So here's the this is the true power, I mean the active power. Yes, we can find the value of watt, and no reactive power. So for the resistive load, this is apparent power equals P, and Q reactive power equals 0. And similarly is for this reverse one. Here is the supply end is Y connected, but here is delta connected, and this is the star connected, so it's just the reverse of this previous math. And it's just a typical distribution scenario from the transmission line via transformer to the house. It's a pole, and this is a guy wire. This is the pole is connected to the ground for the standing. If there is any storm that can't tilt the pole, and this is the grounding cable, and this cable goes to the house, and this is the neutral, and this cable is connected to the transformer. It's a single phase step down transformer. That will connect it to the phase line. So now here we'll focus on the more details on the distribution and utilization. This is the same figure as the above. It's a generator, it's a step up transformer, this is the bus bar, this is the circuit breaker, it's also the circuit breaker for the safety system, and this is a transmission line, high voltage transmission line, and once again this is the step down 3-phase transformer, and this is the circuit breaker, is the distribution line, and once again there's a distribution, or it could be called as a secondary transmission or the primary distribution. And this is the 3-phase step down transformer, and once again the step down transformer for the household, and this is the circuit breaker. There's another connection to the heavy load, yeah, and is this is the illustration of the above figure. This is the insulator, and this is the fuse. This is the lighting arrestor. Lighting arrestor is for when there is a thundering, so for the safety of equipment, it will the thunder, there's a heavy current is there, so lighting arrestor collect all the thundering here. This lighting arrestor is connected through here, and it will connected to the ground wire, so that high voltage is just go through this pole to the ground. And here you see that this is the 3-phase line. This 3-phase line goes into the house. This is the power meter, and this is the distribution board, and this is our premises is connected here. So this is all about the scenario. And the distribution system has two parts. It's primary and the secondary, as I said in the earlier. And the primary distribution site consists of overhead, either overhead or underground cable. So in the urban area, most of the liners overhead, and typically in the rural area there is an underground cable of power distribution system. So the primary distribution side is called the feeder, and the feeder supply the distribution transformer, because there is a step down transformer to the distribution line. So step down the voltage of secondary level, and the secondary distribution transformer, it could be overhead or the underground, depends on the geographical scenario, and it may be the three-phase or single-phase power. Now we see another example. Let's see a DC two-wire system. This is the DC two-wire system is converted into AC three-phase. This is the AC three-phase three wires, and for the DC current is denoted I1, and the for AC is denoted by I2. As three-phase three-wire system, by addition a third conductor here, there is already two conductors. So from two-wire DC system can be converted into three-phase three-wire, just adding another conductor here, and the same cross section of two existing, this is two existing conductor. Calculate the percentage of additional load. So adding this additional conductor, how much this AC system can carry the additional load. Yeah, we have to find the value, and where the voltage between the wire same, and also the percentage of loss remains same, and this is a balanced load. Obviously it's a resistive load because balance, and the power factor is assumed to 1. Now let's see the example for two-wire DC system. This is a power supply P equals VI, because there is no cos theta here, and the power loss for the two-wire DC. So this 2 for 2i, this 2i square r, and the percentage of power loss is the total power, and this is the loss power, and the percentage can be defined as this. For the three-phase three-wire system, P equal to root 3 VI. Here is a cos theta, but cos theta is 1 here for the resistive load, and the power loss for three-phase system 3i square r, and the power loss percentage of power loss can be defined like this. And so according to the condition, the voltage between the wires same, and also the percentage of loss same. This is the percentage of loss for DC, and this is the percentage of loss for AC, and it's same. According to the condition is same, then we can find I2 is 2 by root 3 times I1, and then this is the power for AC and power for DC. We see that. So just adding a additional third conductor with the DC system with the same cross-sectional area, the AC power can carry twice the power of the DC, that is just a double. So yeah, so the additional power is just a 100%, it's just a double. Yeah, so here's the benefit of three-phase AC system. Now this is the factor that affecting the distribution loss. It may be the inadequate by insufficient size of conductor, because the thickness of conductor is important because of the value of current, and the feeder length, as the length of the primary distribution cable is higher, then the loss will be greater, and the voltage, so if for the low voltage the current will be higher, and the I square or the transmission line voltage would be the higher, and the distribution transformer must be according to the specification, and the low power factor obviously needs the larger kV equipment, and as well as the thicker conductor, and it definitely increase the loss as well as the cost. Now we see the classification of primary distribution system. As we see, this is the three-phase AC system. It's a 33 kilovolt. It's a feeder line, and this is the substation here. This is actually the step down transformer here, 33 kilovolt to 11 secondary side is 11 kilovolt, and then it is directly connected to the heavy load, so all are heavy load. So it's called the primary distribution system, and there is a three topology here. It's the radial and the ring and the network. So now we'll see the details. This is a radial. Here is a substation line. There is an incoming line from the two different side, and here OC line is called the radial because it separate the feeders radiate from the single. This is a single substation and feed the distributor. This is the distributor at one end only, and here A point is a one point only. Yeah, and the radial system is employed when the power is for actually the for low voltage end side. So there is some disadvantage of the system because it's just for a single line is connected here. So if there is any fault is happen here, then the entire side will goes down. And in the distribution line, the capacitor bank is placed in the three phase. Here 1 2 3 is the capacitor, is the fuse, it's a fuse, and this is the insulator, and this is the three phase line. Yeah, it's a three phase line. It's a neutral or grounding line is connected here. So capacitor bank, we have to use the capacitor bank for the improvement of power factor because it supplies the negative reactive power that minimize the inductive load reactance effect, and also it reduce the losses, square losses, because for the long transmission line there is a R and inductive reactance is there, and XC is minimize the effect of XL, that is inductive reactance, and reduces the voltage drop, I mean the voltage regulation as well. So here's the advantage of using capacitor bank, three-phase capacitor bank at each phase. Now the second type is the ring or loop system. Here see that there is a single substation. Here they create a ring system. This is a primary. This is the division of primary distribution system. So it's a primary ring here, so it's connected, is drop here M, O and Q points, so it's connected to one distributor, 2 and 3 distributor. In the above one radial system, just one distributor is here. So here's the benefit is that, for example, for this point we can go in this way, so supply can be either two-way. This is S, L, M. If there is any fault happen, this is the fault happen in this point, then the system can provide S, R, Q, P, O, N, M. So here is another path is here. So for the all distribution there is a two possible combination here. So if there is any fault happen in this system, then the other backup path is remain. So it provides the higher reliability than the radial system. And the third one is the network system. Here you see that there is a here is another substation. Here is another substation. The multiple substation can be connected here. This is why it is called interconnected, and it's increased the obviously it increased the reliability, and it's for higher for the higher value of the load. It can be used for higher value of the load. So any area fed from one generating station during the peak load hour. Yeah, so we know there's a different type of power plant we have. So in the peak time, typically in the evening, there's a peak power plant that need to be started, so the substation need to be active accordingly. So yeah, so in the time of peak hour, this type of connection reduces increases the efficiency of the system, and yeah, reduces the reserve power capacity. And in the secondary distribution system in the above, we see that here this is the primary, because all the 11 kilovolt is doesn't anymore to step down, and it's just go through the heavy loads. And then this is the for the secondary system. We see this is the 11 kilovolt line, it's a delta connected, whatever the connection, and then it's go for 400 volt. It's a line voltage, so it's a three phase. It's red, yellow, blue, and the neutral. The neutral color may be the black. It's a black one. And so this is the, you see, this is the line to neutral voltage 230, and this is line to line. The line to line is a root 3 times of 230 volt. So it's for, actually it's for 50 hertz, but in here in Canada it's 120 volt, and it should be the line voltage is 120 multiplied over 3 times. And here is the different household is connected to the different phases, and this is the it's one phase, two phase, three different phases connected. But for the heavy load, for the three phase factory load, because it's a heavier one, and all the three phases connected to here. And for the residential, for the small, for the lighter load, just only a single conductor is connected here. So it's actually defined as a secondary distribution system, and it can be categories into 4 different categories. So first one is individual distribution transformer. Here's a primary feeder is connected from the another line, and then there is a fuse or circuit breaker. Typically it is a circuit breaker, and then the step down transformer, and then this is for load. So it's commonly used in rural areas, and the customer is directly, here is the customer is directly connected to the primary feeder. And the common second one is common secondary main. So here we see that the primary one is actually shared. It's a shared because the common secondary main, here is the secondary, there is a service, there's a different service users, so it use the same. Yeah, it's a several customers share the secondary main, and it's and here is some advantage, that is sudden load change will have less effect on voltage. Sudden load change, like when the large motor starting, it took a large amount of current during the starting. And the third one is secondary network. It's also provide the high reliability, and in the USA most of the cities are connected to this using this connection. And the fourth one is a spot network. Here is a spot network, here is a substation, this is a circuit breaker, feeder, there's another switch or isolator is here because the high voltage transmission high voltage distribution line, so switch is adding for additional safety. And the step down transformer, another network protector is connected to here. So this type of called a spot network. Here you see some example here. So a distribution substation, you can do it by yourself. It's an easy one. And so let me know if you faced any problem. So let's see another big example here. Probably saw the last example. So here is the distribution transformer, is a sending in voltage, and this is the transmission line, resistance, reactance, and this is load in. This is the load in where the inductive load and the resistive load is connected to the parallel, and another shunt capacitor is connected for improving the power factor as well as reducing the loss and improving the voltage regulation. Now we have to find, like this is the given value. This value XL load, R load, and the XC value is 40 ohm is here, and impedance seen by this source without capacitor bank. So for this condition there is no capacitor bank, then the total impedance would be this one in series, but this one in parallel. So here we'll get this one. And for the second one, when the capacitor bank is the capacitor bank is connected, then this parallel is once again is parallel with this, so we'll get this value. So extension of this problem is, let's say the above figure shows a single line diagram of 13.8. This is the 13.8 feeder line. This is the primary feeder because it's feed over here. 13.8 feeder line supply to the load is a load at the end of the feeder, and a shunt capacitor bank is located to the load bus. Here is load bus and shunt connected. Assume the voltage at the sending end. This is the sending end of the feeder is 5% above the rated. So rated one is 13.8 and the sending end voltage is 5% above, and then the load Y connected as our load is 20 ohm in parallel with inductive load is 40 ohm and with the shunt capacitor bank. So condition A, here A, shunt capacitor bank is out of service, so no shunt capacitor is connected here. Now we have to find the line current, voltage drop, load voltage, and blah blah blah. And for the B, when the capacitor bank Y is connected, here is the value 40 ohm, and then once again we have to calculate all these 7 parameters, and in the C we have to compare this result. Let's see the solution. So without the capacitor bank, so there is no capacitor bank. Yeah, the Z total, we already find that the Z total is here, and we have to find the line current. So I equal to V single line to neutral, so divided by Z total is here, but this is the sending in line to neutral. This is sending BS sending in line to neutral, and the value why this is because here we find the line value, so the voltage, this is the line voltage, this is the line voltage, so we have to find the phase voltage. Then 13.8 divided root 3, and it's a reference. Obviously it's reference because all the load are connected in parallel, so in parallel voltage is reference, so we used 0 degree here. And why it's 1.05? because we see that the sending in voltage is 5% above the rated. This is the rated, so 5% means 1 into 5%, that is 0.04. yeah, so here it's a 1.05 multiple by this. Find the line current is here, and the voltage drop is V drop through the line. Here is the line, then this is the Z, so it can be find as I into Z. So Z is 3 plus J6, Z equals, this is the Z line, so Z line equal to R plus JXL. Yeah, so R plus JXL into I line is here, and we'll get this the voltage drop, and this is the load side. How we'll get the equation? This is the sending end voltage. This is the sending end equal to load voltage plus the line. This is the line value, and we'll get the load voltage here. And the fourth one, we have to find the real power and reactive power. So P equals 3 for 3 phase 3V square divided R we already know the value 3 divided, and the for reactive power is 3 divided by reactive for inductive parameter is megavar, and is for megawatt. And the load power factor, we know this is the cos theta, and theta can be found this way. This is theta, this is megavar, this is megawatt, and this is MVA, and we can theta equals to tan theta equal to MVR divided megawatt, because there is no MVA, no MVA rating is given, so we find the value of power factor here. And then the losses is 3I square real loss, and this is the reactive loss 3I square XL, and the real power and reactive power, and the apparent power is can be found as here p square or q square or root 3 pi, anyone, the result would be same. And for the case b with the capacitor bank, for the case b with the capacitor bank, here just change the total impedance here, and all the procedure remains same, and comparing this result. So when we add the capacitor in the parallel with the load in the shunt connected, and the real power is delivered to the 23%, is compare the result from these two. It's 7.43 is real power from the 6.033. And also there is several benefit. All the terms, line current decreases, real and reactive losses also decreases, the voltage drop decreases, and the reactive power decreases, and the load voltage also the increases. So all the parameter we meet. So just doing the capacitor is parallelly connected with the load, inductive load. And the last one is the receptacle in our home appliances. So here this big hole is for earthing or grounding, is for the safety purpose, and this bigger hole for the neutral connection, and this is the phase, this is the main line. So it's called the hot line, and so it's dangerous, and if we touch here, then we'll get a big shock. So thank you. So that's all for today.